All right. Good morning, everybody. Thank you, Prakash, for the invitation to this seminar. My name is Pablo Moriano. I am researcher in the Computer Science and Mathematics Division at Oak Ridge National Lab. And I'm really excited to be here. Today, I'm going to talk about securing automotive networks using data science and machine learning approaches. So before going into the main details of my talk, I would like to make a parenthesis about Oak Ridge National Labs and the Department of Energy National Labs in general. So in Oak Ridge, all this always started 80 years ago as a product of the World War II. So the main goal at that time was being the pioneers by producing the nuclear reactor to end the war, right? The nice thing about this is that after the war ends, there was so much emphasis to continue pursuing research in areas and directions of interest to the government. So probably at that time, that was the major priority. But these days, this is probably the outlook of Oak Ridge National Lab. So I'm offering this view of national labs because hopefully in the audience, there are some students that want to learn more about the complex, what we do here. So I'm going to spend a few slides on this. And these days, we are known because we are hosting the #1 supercomputer in the world, Frontier. But also, we have state-of-the-art facilities in multiple dimensions, such as, for example, the Transportation Research Center in here, so where we do research about reducing emissions to the atmosphere across different applications. And we also host another stellar facilities such as the spallation neutron source. So where we are also pioneers in neutron science and other things such as the manufacturing demonstration facility where we are able to print this car. I think it was from 10 years ago. So we were pioneers in this kind of applications and also some other cool stuff that we are doing here. So I want to reflect on this is that after the war ends, there has been a lot or much focus on driving research at the national level by focusing on priorities. So I'm going to talk about a little more about that. And also with respect to some comparison with academia. So I totally have respect and admiration for our folks in academia, our faculty. For me, they are the guardians of knowledge because they discover basic knowledge, they preserve it, and they also have a pretty amazing mission of teaching to the next generation. Here at the National Labs, we are also a set of engineers and scientists, and we are focused on or more mission-driven on the toughest challenges of the time. So this time, our main occupation or these priorities are mainly driven by climate change, by new ways on how can we discover new energy sources, and also national security challenges. And this picture here in this slide is reflecting one of the main things I like about working in this place, where we basically can be described as bridging the two sides of fundamental science and applied research. So this means that the things that we are doing here are expected at some point to be transitioned to technologies that can be deployed out there. So that's one really special thing that I like about working in a place like this. If there are people more interested about more details, so you can please check out that URL in the slide. So it contains a lot of more details and really cool stuff about learning more about the National Lab Complex and Oak Ridge. So now, with respect to the research and this talk. So I'm going to focus on 2 dimensions of these figures because I think I don't have enough time to cover facilities. But the idea is going to illustrate the state-of-the-art work that we are doing here for securing automotive networks in two dimensions. First, intrusion detection work that we have done in the previous years, and also in the mean of these 2 presentations, I'm going to introduce with a data set that we collect here and we use for our research. So we hope that this data set is hopefully being used by the community out there very widely. So with that, I'm going to start with some vehicle security basics for introducing this topic. And the idea here is that our motor vehicles are basically highly complex cyber-physical systems where there is a technology or a protocol that is called CAN or Control Area Network that allows these what is called electronic control units. They are basically microprocessors that are consuming information about different physical variables about your vehicle and transmitting over the others to have a control of what's going on in the vehicle. So all of these signals that are transmitted by the ECUs are basically using a common bus that is the controller area network. Controller area CAN is not only used for the purpose of vehicles, but let me tell you that it is widely used in other industrial applications or facilities, such as operating rooms, and also in some cases in airplanes. So it's widely deployed in other kinds of applications. And in terms of vehicles these days, even when there are promising technologies to replace CAN, I would say that CAN is the widely deployed and used protocol for vehicles. So this is in the case of passenger vehicles, but also CAN is widely deployed in what is called medium and heavy duty vehicles, in the sense that most of the what can be used for analyzing and studying these events in passenger vehicles can be translated to these more heavy duty vehicles, because the changes in the protocol are not significant from the point of view of analysis. They are just minor changes with respect to the frame definition of the protocol, but it's nothing more than that. I'm just reflecting on this because some other of our applications have been targeting this space of heavy duty vehicles. So even when CAN is great because it's cheap and it's super fast, there are some drawbacks with CAN and some particular things to mention. And is the thing that there is no authentication in CAN. So that may cause, of course, some issues from the cybersecurity point of view. And also there is no encryption. So the main issue about this is to be able to verify that the actual senders of the messages are the ones that we expect, right? In terms of some particularities about this protocol, is about that is related to broadcast network. So these messages are broadcast to the other ECUs in the network. So there is no notion of sender and receiver this information. And from the point of view of manufacturers of these vehicles, of passenger vehicles or heavy duty, the notion of security has been mostly translated to the concept of security or obscurity. So where what they want is to basically being able to obscure some of the information as a way to protect the privacy and in some cases the security of these devices, right? So this is a 30,000 feet overview of what is CAN and what has been done. But now just let me tell you one of the nice things that we do here at the lab at the beginning some years ago, to show you that basically with not much money, nearly no knowledge about this technology and in a motor vehicle, we simply were able to hack one of these. So I'm going to play a short video about this.
Hey, 27 January, this is the NTRC. We're doing a random selected shot of PIDs into the vehicle on a random basis without any prior knowledge of what PID does what. It's just going to shotgun them in. So once we start rolling, you'll see the yellow light. That means it's triggered. Red light means it's set. Starting the acceleration now. There's the green light. It's monitoring. Yellow light's the 10-second trigger. Red light. Now it's going to get crazy. Okay, you can hear that? The hazards are on. Lots of clicking noises and the engine's shut down. You can see foots to the floor, stop safely now. So good times, good times. Here, hold my beer. Now watch this.
So the point with this video was illustrated by that basically no knowledge on how it can work. We simply send randomized messages at a high rate and we're able to deny of service the operation of the vehicle. So basically this is a very simple attack that can be performed in this type of scenarios. So now with respect to the research. So I'm going to introduce our previous work on benchmarking time-based intrusion detection systems and the more advanced version of those that is based on signal-based. And in the middle of those, I'm going to introduce you to the ROAD dataset that I hope is going to be a good reference for you for your research in this area too. So in terms of attacks, Widely recognized taxonomy for classifying these attacks is this three-tier taxonomy from this paper in here. The idea is that there might be fabrication attacks in which basically the adversary is interested into sending or injecting extra messages to the canvas. So of course, this can generate denial of service or through fuzzing or through target ID. The other notion is about suspension, in which they use basically to silence ECUs because they want to basically prevent it to transmitting some information. And the more advanced version of these attacks is something that is called masquerade or falsification attacks, in which basically adversaries are able to impersonate ECUs, and with that impersonation, being able to send fake information in the canvas. So with that, the simplest version of these attacks or fabrication attacks can be understood by this threat model, in which basically we assume that an adversary have access to the canvas. This can be achieved by connecting or plugging a device into the OBD2 port that you can find in your vehicle or through wireless. And here the idea is that, as you can see here in the figure by the red ECU, an adversary is basically interested into introducing data. But what is peculiar about this data is that it's sent at a different frequency of what is expected, as you can see here at the bottom, right? So the main characterization that can be achieved, or effect on the system that can be achieved by this action, is by basically disturbing that frequency of those messages. So by relying on that notion, what we did was to focus on a way on how to effectively detect those and do a comparison of different kinds of those detectors. But before that, with respect to detection, this is a very nice summarization of the taxonomy of how can we detect those attacks. So in the canvas, so it can be made through basically rule or specification or whitelisting. Of course, all of these have advantages and limitations, but just for your reference, or side channel has been all research focusing on mining physical layer attributes such as voltage in this network to get to identify these attacks. Here, our focus was mostly on the fact that I show you about affecting frequency and how can we leverage that understanding for the detection. And lastly, for the last two, payload and signal, those are mostly related and focused on the advanced cyber attacks or the masquerade attacks, the falsification attacks, because what we are interested in that is to mine information that is being transmitted into the canvas. So I'm going to go to that later in this presentation. But for now, the focus is on frequency methods. With that, we here at the lab have the ability to collect this data in a controlled environment. So we have here a vehicle security lab where we're able to basically, by using experimental design, to think about different attacks that we can perform in the vehicle and actually deploy those attacks and collect the data in an actual vehicle in a controlled environment by verifying that the attacks were actually being represented in the vehicle. So this leads to this work that is in peer review now. The link to the data set is in that URL. But basically, the idea is that we're able to collect over almost 3 hours of data in benign conditions in a dynamometer and also in the road. And also for the case of the attacks, we were able to collect different types of attacks, including basically affecting the correlation between the speed of the wheels, and also the engine temperature of the vehicle, the speedometer, and the lights of the reverse lights. So all of these almost comprise about 30 minutes of data, of attack data. So this has been widely being used lately in the community for testing this kind of works. So as I mentioned to you, most of this data is collected in a dynamometer. We count like six different types of attacks that are targeting 2 of the IIDs. So here the notion of IID that you also heard in the video is related to an identifier of the brain. Is nothing more than that. And basically here we're interested in the process of intrusion detection. So we want to label frames that are basically malicious if they are found in the attack interval. So we know the ground truth of the attack intervals because we introduce attacks. and otherwise one of these brains are labeled as benign. So with that notion, remember that the focus on here is on the frequency, on understanding that frequency on those messages. So here we show here in this figure an exploratory analysis of that frequency for one of those IDs. In the left figure, what we show is that for a single ID, what is the inter-arrival time distribution for those messages in the log scale? As you can see, that is pretty spread across the time domain. But just by removing some of those outliers by using minimum covariant determinant, we're able to show the figure on the right. So basically showing that there is that this inter-arrival time distribution can be characterized by some mathematical function. So that's our intuition of how can we detect these attacks here. So the contribution on this paper is the following. The reference is in the below this slide. So we focus on comparing unsupervised, very simple anomaly detection methods. This is important because our notion here is we can create something very sophisticated, but we're also thinking in ways on how can we translate this research into practice, so something that can be deployed in actual vehicles. And the methods that we compare are four. The first one is about the mean inter-message time. I'm going to explain each of those later. Binning, that is basically counting messages. And the last two are about fitting probability distributions in distant inter-arrival times using Gaussian distribution or kernel density estimation. For the sake of presenting these results, let me tell you that we micro-average the results over the attacks in our data set. And here the notion in the figure below is that what we are trying to detect are those red points that are basically the malicious injected frames in the canvas. So for that, for method number one, what we did was, of course, this is the easiest option, was to empirically compute the mean of these messages during training. We also define a notion of a threshold alpha here. It is basically the percentage of time that we are willing to accept as a reference for labeling that as an attack or not. For each of those IDs, basically we compute that distribution and check if in empirical data that distribution is lower than certain threshold. So that's the function of alpha in this simple model. And we basically mark an attack if at least 3 out of the 6 interframe arrival times are less than this condition. So with this very simple approach that is just measuring this inter-arrival time mean, we found these results on this type of attacks. Of course, the idea of this work, more than presenting this, is to compare to the others. So now I'm going to talk about the other methods. The second method that we consider is we call binning, and the idea here is that we are going to count the number of messages in time windows that we define of certain length. So we are going then to vary or imagine that we have a window that we can vary in certain length that we can parameterize by this parameter alpha. And what we can see from the empirical data, the training data, particularly in the ROAD dataset, is that it's very unlikely that you are going to find in a window of certain length more than 5 messages or 1 or 0 messages. So it's very unlikely. So most of these messages, or in more of these windows, you can find between, I would say, 4 and 5 messages. So that's what you should expect in this scenario. So this is a little bit different from the previous, in which we need to have a notion of counting messages, but still it's really simple in terms of implementation. So when doing this, we found empirically that we define that there is a threshold that we can also basically impose by manipulating this parameter alpha. And what we found is that the optimal alpha is about between 3 and 4 messages in terms of the length. What we found is that by using still this really simple approach, we can increase the performance metrics for this detection in terms of this scenario. The third approach, remember here that the notion of understanding the inter-message distribution time of these CAN frames. So as we saw in one of the previous figures, it looks like there may be very well represented by a Gaussian distribution. So in that, what we did was to empirically feed that data with a Gaussian distribution. With that Gaussian distribution, being able to spot anomalies if they are basically very unlikely to belong to the Gaussian distribution, basically using the notion of p-values. So here, the idea, again, as marked as an attack is at least 3 of these consecutive intermediate signs are less than the condition. So we have still the notion of these thresholds. And even when we optimize these thresholds for the data that we have, you see that there is a significant drop in performance comparing this with the 2 others. So that is resembling basically that even when visually this may seem like Gaussian, there might be some other nuances in the data that are not very well represented by that distribution. So to cope with that concept, we were able to account for a non-Gaussian distribution. So basically another more generic distribution that allows us to fit that inter-arrival time distribution. And for that purposes, we use kernel density estimation with a Gaussian kernel. So here the idea is pretty similar to method 3, but instead of Gaussian fitting, it's kernel density estimation. And we also have the notion of having these thresholds that allow us to control how good is the detection or not. And here the detection criteria is also at least 3 of these consecutive inter-messages times are less than the condition. So when we do that, we improve a little bit over method 3, but when compared to the previous two, with the first 2 methods, is generally a significant drop in performance. So as a summary of our results, we were interested in comparing very simple approaches that focus on detecting these fabrication attacks. Remember that the notion of fabrication attack is being able to disrupt the frequency of the messages. The reason we want to do this is because we want to have a way to translate these methods in algorithms that can be deployed in edge devices that can be plugged in vehicles. And by the way, this benign method that was the front runner in this comparison is actually being deployed in some of the vehicles that we have here as a test in the lab. And so the benign was the front runner method. And the second best option was the mean method because in terms of performance, it's the second, but it's a little bit faster than the mean, and it's really straightforward to implement. So neither the Gaussian or the KD seems to be good options for this problem. When we compare also with respect to several thresholds in this domain, so figure A here are showing the conditions when we have outliers. So remember that we can have some outliers in this data. So if we have outliers, still the binning method is the winner. What is shown here in the table in the right. These percentages are basically the area under that curve, basically the precision and recall curve to account for the cases of imbalanced data set, as in the case of intrusion detection. And the figure on B on the right is basically representing the case where we remove some outliers. So you can see that when we remove outliers, some of the other methods start improving, but still the binning method is outperforming the others. So just for reference on terms of comparison. So that is with respect to frequency or the simplest attacks in the canvas. How can you understand simple methods that can be easily deployed in the field? But now I'm going to focus on the signal-based attacks or the masquerade or the falsification attacks that are the more stealthy in this nature. So remember here that the idea is that an adversary is going to be able to, we assume that is gaining access to the canvas. The main notion is that the adversary is going to impersonate an ECU and is going to basically send fake information about the vehicle. Why is this important? Because if you are in your vehicle, an adversary is able to launch off these attacks. has been shown that, as is in the figure in the top right, this can be used for nefarious purposes such as manipulation of your vehicle. This happened a few years ago. Basically started a lot of research in this area. So basically, the adversary can get control of the signals of the car and manipulate it at their own will, which is pretty bad. In terms of how this works, the idea is that an adversary, of course, needs more knowledge about this, needs more time and money to launch this kind of attacks, because first, one of the ECUs or the target ECUs needs to be silenced. So suppose here that we are going to silence, or the adversary is going to silence ECU B, but there is ECU B, but by using another strongly compromised ECU, the adversary is going to introduce fake messages. The important thing here is that the main difference with the previous attacks is that they kept the frequency the same. So these kind of attacks are not going to be detectable by the other approaches. So what we did here is then focus on analyzing if payload or signals are going to be effective for these purposes. What we found is that if you use payload, it's basically focused on the bit representation of the data. But there is, of course, a semantic gap because we don't know the signals that are being sent. But more importantly, we don't know the correlations between those signals that are super important for this detection. While in the case of translating the CAN signals into real values is appropriate for capturing correlations, although in the current state of the art, they are expensive, focus on deep learning machinery, which are not going to scale so much with the hundreds of IDs that you find in your vehicle. So in this paper, best paper was AutoSec in 2022. We focus on proposing a way to address that from a forensic point of view. So here we assume that we can have access to the logs of the CAN data post-mortem. So there has been some driving and then some collection of that data. We were interested in to see if by mining that data we can detect these attacks. So we propose basically agglomerative hierarchical clustering methods that basically do hypothesis testing to compare how dendrograms are similar or not. For that, we perform some sensibility analysis over several linkage functions to see which one was the best working on this data. And we focus, of course, in our ROAD Dataset because it contains real verified attacks. So here the notion is the following. So in figure B, what I'm showing is a dendrogram of a toy model. So consider that originally we have 4 time series that are placed in the x-axis. And in the y-axis, what I have is a notion of distance. Distance basically means how similar are those series. So this B figure can be translated into the A figure by looking at the color. So basically, originally, each of those signals are their own cluster independently. But as you start varying the distance, or basically being more willing to accept that the similarity of the signals can be different, you can start basically cluster them together. So at some point, for instance, when you increase this distance, series 1 and series 4 are going to be their own cluster. If you continue increasing that, series 2 and series 3 are going to be their own cluster. But if you still consider increasing that, at some point, all of these signals are going to belong to a single cluster. So this is super important because here our assumption is that when one of these attacks is launched, it's going to change the correlation of the variables because the adversary is willing to change the messages, right? But we expect and we don't assume that the adversary is going to know correlations internally on the vehicle. So that's a really sensitive thing to know from an adversary point of view. So with that notion, once we build these dendrograms of this time series, we are able to compare how similar are those dendrograms using a very nice method in this paper. So basically, this method is telling you how similar are dendrograms. So it produces basically a number between 0 and 1, where 1 is more similar. So here, for instance, A and B are more similar than B and C. I mean, you can see here visually why is that the reason. And we developed basically a hypothesis testing approach that allows us to compare distributions of similarity. So consider here that in our experimental design, we have benign files. So we have 12 of these benign data collections. And we have, let's say here, 3 of these scenario attacks. And we are going to compute the distribution of these 66 possible combinations, pairwise combinations of these with each of the scenario attacks in here. So at the end, what we have are comparisons between distributions of similarity of dendrograms, and if the dendrograms, our criteria is that if the dendrograms are so much different, it's because there might be from an attack. So by using that approach, we found that when we use agglomerative hierarchical clustering and the word linkage, that is basically a way on how can you build this notion of nested clusters. We obtained the best results here. So of course here we define our p-value being 5%, but in the word linkage scenario, we found that it's able to detect all of these types of attacks. So it works better than most of the others, followed by complete linkage that miss one of those. We were also to test that the discriminatory power of these techniques depends on how or how many correlated signals are affected. So basically, when only one signal is not affecting many of the others, it's going to be very hard to be detected under the assumption of our method. And as a summary of our results, when we were able to run cross validations by letting 3 benign files apart and basically rerun the experiment, we found for the best linkage this result. So basically, we can get as high as almost in the majority of these cases over the 90s for detecting these attacks. This is promising because it's showing you that by using this notion or this assumption of correlations between signals, you can get deeper on the detection of these really advanced cyber attacks. So as a final remarks, our framework effectively detects these CAN Masquerade attacks by relying on agglomerative hierarchical clustering of time series. So here the notion is that we are able to translate CAN bits into series. If you want to learn more about that, that's a good question for the Q&A. Also, in terms of we build these dendrograms and we compute similarity, and that's the basis for our hypothesis testing. And we also found that the discriminatory powers of these techniques depends on the linkage being used. So look, in our experiments, words linkage works better. And the impact is going to be all related to the number of signals that are correlated. So it's easier to detect when more of the correlated signals are perturbed. So in our experiments here, you'll see that one of the best results is obtaining this correlated attack. So this correlated attack is basically when we are able to inject these messages that change the correlation between the wheel speeds in a vehicle. So in general, you will expect that there is a close correlation between the 4 wheel speeds in your car, right? But in this attack, what we did was distort that correlation. In that correlation, so speed is in your vehicle is related actually to many other variables. So that's the reason it's obtaining better results, while the others, speedometer or temperatures in the coolant are in the engine you would expect that are probably less correlated with other variables. So that's what we found. And actually, our focus has been on basically deployment of this algorithm into a more real-time fashion. So we are working on this actively because, again, our purpose is to be able to translate this into something practical that can be plugged into vehicles out there. So with that, I think that I'm almost getting to 40 minutes. And last but not least, I would like to thank the amazing team of collaborators here. So that are listed in this slide. Also, some programmatic help from these other people. And also this part of this research has been funded by the Laboratory Directed Research and Development Program at Fabrication National Lab, which is an internal fund for projects. And I also have a set of pictures that I don't have time to show now, but this was basically some of my collaborators in the background in the vehicle security lab, where we collect this data, where we inject the data. This was a few years ago here in the lab. And with this, I conclude my presentation. There is my contact information, and I'm more than happy to take your questions. So thank you very much.
Two so much, Dr. Pablo, for your insightful presentation. And I think it's nice to see the two different research framework that you talked about, on simple versus the signal analysis. Let me start by asking some questions in the data set that you're dealing with. For example, correct me, it is, I know I had a group who was my PhD student, has done some work on ECUs, and how do these ECU IDs are proprietary commercially in these vehicles, right? So I think, have you done any, what is your take on actually, is there a problem space, first of all, detecting, the ECU IDs using signature based, whether it's braking, steering, there are some signatures you can able to say, what that may look like. Each of those, different types of vehicle make, I think they may have, so I'm just curious to see, have you done work on actually, I'm not sure about this ROAD data set that you're referring to. Looks like it has already labeled data sets. Probably you have used this labeled data sets, or is it something that, real-time data sets? Could you shed some light into what I'm asking here is actually, which ECU IDs was easier to detect versus which ECU IDs were, challenging? You talked about correlated, I want to just first see what is your thought on that.
Yeah, so actually reversing engineering those signals or IDs is a really tough problem. And I will spend more presentations of that. By the way, I have some backup slides about that, but to get more precise about your questions about the ROAD dataset. So we provide the labels in terms of specifying the start and the end of the attack, and the IDs, or the ID that is basically injecting the attack. So that's the type of labels that we offer in the data, in the ROAD dataset. We do not offer in the dataset like the meaning or the semantics of all of the signals in the CAN bus, but we offer for sure the basically the label of the interval time and the ID that is introducing the problem. So that's one part of, I think, of your question. So are you still seeing my screen?
Yes.
With respect to, I think, with your second part, this other work that was done by other collaborators in here, and I want to highlight that because it's super novel work. That is the problem of decoding those signals into the CAN bus, right? So I didn't talk about this in this talk, but here the idea is that you have basically these 64 bits encoded into the frame, and you don't know the meaning or the semantics, right? But what they did with this work was basically to reverse engineer, and it works pretty well under certain conditions, about being able basically to say from bit 0 to 7 is going to mean engine RPMs, or you can imagine the others, right? So these are really tough problems. And their focus was on basically use an algorithmic pipeline based on machine learning, on supervised machine learning. So the way, how do they correlate the bits with the semantics is by querying actively the CAN bus for some specific messages. So there is a mode in the CAN bus where you can query the bus and you know the label. So you can query, okay, give me please the, I don't know, the speed or the temperature. So by looking at that process and by correlating with their pipeline, they were able to have some estimation of what signal can be, for instance, the accelerator pedal position, the vehicle speed, the engine RPMs, and all of that. So in other words, this algorithmic pipeline is able to produce a DVC file. That is basically what you need to decode your data. So this work was published last year, I guess, it's already published in IEEE transactions on transportation intelligence systems, I guess. And I think that there is they also commercialize the license this technology, but there is also an option for an open version of this. So I don't know the precise details of how to get to that, but if you are interested, let me know. I can put you in contact with the people that is in charge of this.
Good. Thank you. And I know that, let's see, Jameson, do you have any questions coming up? And I'm not sure participant can able to use the chat. I think Eric and Nirup is there, so they both have done some CAN work.
We have one question.
Yeah. So Nirup has a question. How much do you think an alpha value determined specifically for this application can influence the results? I know alpha equals 0.05 is most commonly used for most applications, but please share your thoughts.
That's a really good question. So usually what we observe our criteria for defining that threshold is based on what we observe from the experiments. So it looks like it's pretty conservative to choose 5% because based on the experiments that we run, it's very unlikely that under those conditions you are going to miss an attack or misclassify one of these attacks. Of course, you can vary the criteria or that threshold for more fine or fine-tuning that decision criteria, but of course, it's going to have an effect on these results. So it's always a matter of experiment on empirical data. How can you obtain these better results? But yes, it depends on that parameter specification.
Great. Are there, and as more students are listening to, in the webinar, I was wondering, do you have any advice and directions for graduate students to see what type of data sets or for particular areas of research problems within the vehicular cybersecurity domains? What is your couple of, advice or directions for graduate students in this area who is looking at a thesis topic or dissertation topic on this area?
So I would say that there is a few key elements. There might be, of course, notion and passion to be involved with being able to engage with vehicles and understand and learn how to collect this data, how to introduce these cyber attacks. So you see from the video in my presentation that even with a small budget and almost no knowledge, you can basically launch an attack on this. But it's going to be super important to get hands-on on data collection. How can you interface with the vehicle for the data collection and the understanding of that data? From the point of view of research, I'd say that it's super important to be aware of the state of the art in this topic. So this is a hot topic these days. Research is coming every week or many papers are being launched. So being aware of what is out there and what is like the niche or the space where you can make a contribution, because you don't want to duplicate work that has been done, right? So you need to have a very good understanding of what's out there and how can you contribute to the problem is also really important.
Great. Thank you, Pablo, for your time. I think, you will receive a plaque from UND and for your time and contribution for this webinar and also certificate. And then we should.
Thanks, Prakash, again for the invitation. And let me tell you that if there is any student out there interested in this type of research on in national labs in general or in Oak Ridge, feel free to shoot me an email. I'm happy to talk. I know that from my experience in academia, sometimes national labs are not in the radar of students, but are also a really good opportunity for careers. So please be aware of that. And yeah, don't be shy.
That's great. I know that I have my own students already working now full-time at PNNL and ANL, different labs already. So I think, I think National Labs has been a great resource or opportunity for career that's either through internships or a full-time job. So I think that's great. And Thank you so much. I would